Okay, so we're going to pick up talking about autoregulation. And earlier I mentioned how tissues can recruit their own blood flow. That's kind of interesting. And one of the ways this works is that we can see automatic adjustments in vessel diameter to help meet a tissue's like sort of needs, if that makes sense. So if a tissue is more metabolically active, it will stimulate vasodilation of the vessels that serve it. If you vasodilate, then you increase blood flow to that tissue, which then can help meet or match the metabolism of that tissue. If a tissue is less metabolically active, that can lead to vasoconstriction, and therefore you don't need to send as much blood flow to a tissue that's not as active, right? So it's kind of cool. We call that autoregulation. And there's other mechanisms of autoregulation for blood pressure too. Because if you think about this, remember blood pressure was where fluid is sort of expanding on a vessel wall. And if you think that blood pressure then would cause vessels to stretch, and it does, but what's cool is that when vessels get stretched due to blood pressure, they also correspondingly contract due to that stretch. So we call it the myogenic mechanism. We'll talk about that here in a minute, where you would expect blood pressure itself to kind of blow out your vessels, right? It should actually kind of expand on those vessels and cause them to stretch. And it does. However, that stretch, like I just said, stimulates the muscle to contract and therefore keep the shape of that vessel under changing blood pressure conditions. Yeah.
Would autoregulation be like if you just did right-handed bicep curls?
Yes.
Tore the bicep muscle that now requires more blood to repair the muscular tissue?
Or like if just even before the tear, let's say if you're only doing one arm, like just, let's say if you're like an arm wrestler and you just want to get one strong arm, right? You don't even care.
Arm and you're trying to rebuild it.
Yeah, and you can increase blood flow just to the muscle of that arm, not necessarily both arms.
So that's the autoregulation. It'll just send it to where it's needed.
Exactly, yeah. And that's based on different metabolic factors we'll talk about here in a minute. But that would stimulate vasodilation, which would increase blood flow to that organ or tissue. So there's two types of autoregulation. We got metabolic controls and myogenic controls. The myogenic controls are based on stretch of vessels, and this is a way to help maintain a steady amount of blood pressure, even though the tendency is for blood pressure to cause your vessels to stretch. You'd want to contract then to prevent those vessels from getting too wide due to blood pressure itself. Bless you. And the metabolic controls are going to increase or decrease blood flow based on the metabolic needs of that tissue. And it's a mixture of both, you guys. So up here we see the factors that stimulate vasodilation. Down here we see the factors that stimulate vasoconstriction. So let's first talk about those metabolic factors here. So earlier we mentioned how if a tissue is more metabolically active, you'd want to increase blood flow to that tissue and therefore vasodilate to do that. So you might wonder, well, what are the factors that stimulate vasodilation in a tissue that's more metabolically active? Well, if it's very metabolically active, O2 levels will be low, right? You can expect that because the tissue's using oxygen very rapidly. CO2 levels will be high because you're going to generate a lot of carbon dioxide in response to this increased metabolism. We know that when CO2 dissolves in water, it forms an acid called carbonic acid, which is why we see an increase in hydrogen ion concentration. We can also see an increase in potassium concentration in the tissue surrounding a blood vessel due to an increase in metabolism where sodium potassium pumps aren't working that fast. So these are the metabolic factors that stimulate vasodilation, and that makes sense. Let's say if your muscle tissue had low oxygen levels, well, then you want to vasodilate, increase blood flow to that tissue, that way you can get oxygen levels back up. Or if a tissue is very active and you see carbon dioxide start to build up in the tissue, you'd also want to increase blood flow to that tissue to help eliminate that waste, carbon dioxide, and deliver more oxygen to that tissue. Now, other vasodilators include things like prostaglandins, which are released during the inflammatory response. So inflammation, that kind of redness and heat you get with inflammation of tissue, that's due to the prostaglandins being released, which increases blood flow. And the whole point of that is to help bring in nutrients for tissue repair. Nitric oxide is also released by certain tissues during the inflammatory response, but to also help regulate things like blood pressure. Nitric oxide is also a potent vasodilator. This is why they give people nitroglycerin, if they have heart conditions. Let's think about this. Let's say if they have ischemic heart disease where their heart muscle is not getting enough blood flow. Well, if you take nitroglycerin, that can be converted to nitric oxide in your bloodstream. And if nitric oxide is a vasodilator, that means you can vasodilate the coronary vessels on your heart to increase blood flow in the heart muscle. So if someone's having a heart attack due to ischemia or lack of blood flow, they can take nitroglycerin to increase nitric oxide production to stimulate vasodilation and therefore increase blood flow. So that's kind of cool. And then adenosine is the byproduct from ATP. If you got a lot of ATP use, you're going to see a lot of adenosine buildup, which would also function as a vasodilator. Now, some of the neuronal controls of vasodilation would be a decrease in sympathetic tone. So if you're less sympathetically active, that also stimulates vasodilation. And then we have a hormone here that's also a good vasodilator, atrial natriuretic peptide, also called atriopeptin. This was released by your atria in response to stretch, right? And you'd expect to see that if your blood pressure was high. So if your blood pressure is high and your atria are stretched, they release that hormone, ANP, atrial natriuretic peptide, which stimulates vasodilation, which also therefore decreases your blood pressure. So that's pretty cool. In terms of the vasoconstrictors, what we find that is neuronally, we see an increase in sympathetic tone. If you have more sympathetic activity, that stimulates vasoconstriction. And if you vasoconstrict, what does it do to resistance of the vessel? Increases resistance, which increases blood pressure. Very good. Other vasoconstrictors we talked about, angiotensin II, epinephrine, norepinephrine, antidiuretic hormone. So where do we get angiotensin II from? Yeah, it came from ACE, which converted angiotensin 1 to 2, right? So, and ultimately that came from the kidneys, where if blood pressure is low, then the kidneys release renin, which leads to the production of angiotensin 2. But remember, one of the effects of angiotensin 2 is also stimulate the release of ADH, or vasopressin, and that's also a vasoconstrictor. Now, epinephrine and norepinephrine we know are sympathetic hormones, and that kind of coincides here with the increase in sympathetic activity, which would also cause vasoconstriction. What's also interesting here, you guys, too, is that there's a myogenic mechanism, and this is a way to maintain a steady blood pressure. So earlier I mentioned how blood pressure is fluid pressure, which is kind of expanding from within a vessel outward. You would expect then that due to blood pressure, there would be a tendency for blood vessels to be stretched or dilate, right? Which then would decrease blood pressure. So then you'd have a lot of trouble getting your blood pressure up, right? If every time you started to increase blood pressure and it causes vessels to stretch, then it's kind of like vasodilating. So how do we prevent that then? Well, due to stretch of the vessel, we get this myogenic mechanism here that stimulates vasoconstriction, so that you get a corresponding amount of constriction of the muscle in response to stretch on that vessel. That way you can keep the vessel the same shape even though your blood pressure is increasing. It's pretty cool. And that's that myogenic mechanism, you guys. Now, there's also endothelins that are released by cells in nearby tissue, and they also help to vasoconstrict. So the long-term mechanism of autoregulation we call angiogenesis. This is going back to your question earlier about like bicep damage. Let's say if you're doing bicep curls because you're like a world-class arm wrestling champion or something, and you tear a muscle, right? Well, in the long term, what you get then is new blood vessel growth. So you get more blood vessels that grow to that damaged tissue, or if you start using a tissue more, that can also recruit more blood vessels to grow in that damaged tissue. Or that's just the tissue, sorry. And we call this process angiogenesis. Angio means blood vessel. Genesis means to create. So angiogenesis means the creation of new blood vessels in a tissue. It's a long-term mechanism of perfusion. So what happens then, you guys, is that hypoxic tissues, or tissues that have low oxygen levels, can release hormones like vascular endothelial growth factor, VEGF, which recruits new blood vessel growth into the tissue. So let's say if you start using a muscle a lot and you're achieving anaerobic activities, right, where you get really low oxygen levels, then that tissue that has low oxygen starts releasing hormones that recruit blood vessels to grow in that tissue, which improves blood flow, and then you get better performance in the long run. We call this angiogenesis, so new blood vessel growth. Now, very vigorous cancers do a good job of also stimulating their own angiogenesis, because if it's a cancer and these cells are dividing rapidly, well, they're going to need nutrients, right? Now, if these cells can actually recruit their own blood vessels to grow in, then they can actually grow more quickly. Not just cancer, just tumors in general. Otherwise, if a tumor doesn't recruit angiogenesis, like its own blood vessels to grow in, it can kind of burn itself out, where the cells divide, and because they divide so rapidly, there's not enough nutrients in that local area, so then the cells actually die, which is interesting. So You'll see this commonly like in the heart if coronary vessels get blocked, or throughout the body in people like in high altitude areas. In fact, this is why the Olympic training centers at Mile High, right? Isn't it in the Springs or something?
Yeah.
Colorado Springs. It makes sense because if you start training at altitude, then you can stimulate angiogenesis in your tissues, which means when you go back to sea level, you got even more blood vessels in your tissues that you would normally have at sea level. So you can. It's kind of like natural doping. Yeah, exactly. Just due to geography and our own body's mechanisms. And so you can improve performance that way. It's a good point. Yeah, exactly. Yeah. Start doing like push-ups at Mount Evans, or they got that marathon up in Leadville, the Leadville 100. You run 100 miles up by Leadville.
They do the Pikes Peak Marathon every year too. You run to the top of Pikes Peak and back down.
Oh, yikes. Good for them. I can't do that. I'd die. So earlier we mentioned how capillaries were involved in exchange of nutrients and wastes. And we talked about how capillaries were particularly capable of nutrient and waste exchange because the walls of those vessels were very thin, right? So because those vessels are very thin, diffusion occurs easily across the vessel wall. And we talked about how diffusion is a process where molecules move from high to low concentration. So if oxygen's in higher concentration in your bloodstream, then it's going to diffuse out of blood into tissue where it could be in lower concentration. And that can occur really easily at a capillary, right? Because the walls are so thin. Same with carbon dioxide. Let's say if CO2 is in really high concentration in your tissue, then you can actually diffuse into your bloodstream where it's in lower concentration to help eliminate that particular waste. And CO2 is a waste. It's one of those metabolic wastes that has to be eliminated from your body. Otherwise, it forms an acid that can start to damage your body's tissues. Other lipid-soluble molecules can just diffuse across this capillary membrane really easily. Water-soluble solutes can cross through clefts or fenestrations, and larger molecules like protein can be actively transported, using vesicles of some sort, like transcytosis. So we talked about how there's different types of capillaries, and this particular type of capillary is the fenestrated variety, right? Because we see there's lots of those little holes here. And these fenestrations or holes allow for increased exchange of materials from the tissue into the bloodstream and vice versa. Now, these fenestrations are small enough to where entire blood cells can't pass through, right? We see that. Obviously, this blood cell is very large in relationship to the fenestration. But these fenestrations are large enough to where molecules and smaller ions and water can pass through, if they're small molecules. Otherwise, we can also see that there's transport between cells too, like where the cells meet. We call this intercellular junction. Molecules can be passed between these cells, into or out of the blood vessel, which we see here. Like these intercellular clefts can help transport materials, or the fenestrations as well, which are basically just little pores. Now, what we see here is a basement membrane that surrounds this blood vessel. Remember, basement membrane functions a lot like a filter. Because basement membrane is just basically a big old network of fiber, collagen fibers and that kind of stuff, it's going to trap molecules that might cross that are too large. So even the basement membrane functions like a filter here. So only water and small ions are going to be able to pass through. So what this slide is showing you guys are the different mechanisms of transport. So you can see that molecules can just move directly through fenestration pores. They can move between intercellular clefts. They can diffuse across membranes if they're lipid soluble. They can be transported through vesicles as well. And these are just showing all different ways that transport occurs across capillaries. And it makes sense. You need a lot of transport of materials and nutrients and wastes. So there's lots of different mechanisms to achieve that. Now, one thing that's important to talk about, you guys, is sort of water balance in our body. And because water can move across capillary walls, we got to make sure that not too much water moves across your capillary walls in your tissues, and you get some reabsorption of that water back in the bloodstream. We call this bulk flow, where it's the movement of water across capillaries. Okay? Now, bulk flow is where fluid leaves at capillaries. It can actually either leave the bloodstream into the tissue or go from tissue back into your bloodstream. And there's two main forces at play: hydrostatic and osmotic pressures. Hydrostatic pressure is a fluid pressure, like compressed fluid will want to expand. So an example of hydrostatic pressure is blood pressure, right? So you're going to find there's blood pressure inside of the bloodstream in your capillary. and that's going to have a tendency to want to expand outward and force that water out of the vessel into the tissue. Tissues can also have pressure too. Like where you guys are sitting down right now, like on your butts, there's pressure in the tissue, right? Because you're sitting, and that pressure is in the tissue, but that can also force fluid back into your bloodstream because it's fluid pressure. We call that hydrostatic pressure. So it's a fluid pressure, and it's kind of a pushing force. So when you think of hydrostatic pressures like in your blood or in your tissue, it's a pushing force where it's going to push water in a particular direction. Okay? Osmotic pressure is a pulling force because osmosis is where water follows solutes. So if you have solutes in your bloodstream, that can exert an osmotic pressure, which basically pulls water into the bloodstream. It can attract water from tissue into your bloodstream. Or if you have solutes in the tissue, it can actually attract water from blood into your tissue. And it's a balance of these forces. You got pushing and pulling forces that are having water move in a variety of different directions. And you want this to be balanced very well, because if it's not, then you can get an accumulation of water in your tissues to an excess amount, which we call edema, or you can lose too much water from your tissues, which can dehydrate those and lead to a variety of problems. So this balance of forces we'll talk about in the next couple of slides. But remember, we had hydrostatic pressure and osmotic pressure. Which one's a pushing force? Hydrostatic, right? Which means that osmotic's a pulling force. So if you have solutes inside your bloodstream, like albumin, that can pull water into your bloodstream from the tissue, right? Or if you have solutes in your tissue, that can pull water from blood into the tissue. That's osmosis, right? A pulling force. But we still have hydrostatic pressure, which is more like a pushing force, where water can get pushed in a particular direction. Like blood pressure will have a tendency to push water out of the blood vessel into the tissue. Okay? So what we're going to do here is summarize these forces. So the first one to talk about are the hydrostatic pressures, the pushing pressures. So we have capillary and interstitial hydrostatic pressure. Capillary hydrostatic pressure is actually basically blood pressure, and it's where fluid gets forced out of the bloodstream into the tissue. That's capillary hydrostatic pressure. Now, it's greater at the arterial end than it is the venular end because blood pressure is higher at the arterial end than the venular end. But the net tendency due to capillary hydrostatic pressure is to force fluid out of blood into your tissues. Okay? Now, if that were the end of the story, that means your blood would dehydrate really rapidly. Right? You're losing a lot of water in your tissues, and then your blood volume would decrease, your blood pressure would decrease as a result. Now, opposite to this, then, we also have an interstitial fluid hydrostatic pressure. Remember, interstitial fluid is a tissue fluid, and if it's a hydrostatic pressure, it's a pushing force, right? So interstitial fluid hydrostatic pressure is fluid pressure in the tissue that has a tendency to want to push water from tissue back into your bloodstream. Now, normally this interstitial fluid hydrostatic pressure is close to zero, but you can increase this pressure by like squeezing on a tissue. This is the whole idea behind compression socks. So if someone wears a compression sock because of edema on their legs, then what you're doing is you're squeezing on their tissues, which increases interstitial fluid hydrostatic pressure, which can help push that water back into their bloodstream out of the tissue to help reverse some of that edema. And so you can do it externally, sort of medically, if that makes sense. Otherwise, this interstitial fluid hydrostatic pressure is pretty close to zero because of lymph. So we know that our lymphatic system also carries fluid away from tissues, which we'll talk about here in a minute. What about the osmotic pressures, you guys? Are they pushing or pulling? Pulling. So if we call it a capillary colloid osmotic pressure, if it's osmotic pressure that's in the capillary and it's a pulling force, which way would capillary colloid osmotic pressure pull water? You got it, into the vessel. Because it's a pulling force, it's in the vessel, it's going to pull that water from the tissue into your bloodstream. And guess what, you guys? It's albumin. So albumin is the main solute that exerts this capillary colloid osmotic pressure. And we've learned about this prior in the blood system, where we talked about how albumin helps attract water back into your bloodstream. And if you didn't have this force, then you can start to lose excess water in your tissues. Albumin is a plasma protein made by your liver. So in individuals with liver failure, they might not make enough albumin to hold on to their blood plasma, or they can lose water now in their tissues. Now, so keep that in mind, you guys. Capillary colloid osmotic pressure, it's a pulling force where it's going to pull water back into the bloodstream. What about interstitial fluid osmotic pressure? Well, there's solutes in tissue too, and that those solutes can actually pull water out of blood into the tissue. But you guys see how low this pressure is, though? It's pretty much close to zero, like 1 millimeter of mercury versus 26 millimeters of mercury for capillary osmotic pressure. So interstitial fluid osmotic pressure is pretty low, but it can get higher if someone has a lot of solutes in their tissue, or if their blood vessels are leaky and they start to lose albumin in their tissues. That albumin can now start to attract water into the tissue because that's where it is, right? So what we call then, you guys, all of these forces added up is net filtration pressure. So let's summarize this sort of equation here. So net filtration pressure tells us about the movement of fluid across capillaries. So which way does hydrostatic pressure of a capillary move water? Out of the blood vessel into tissue, right? How about osmotic pressure of the interstitial fluid? Also out. Remember, because osmotic pressure is a pulling force, but if it's in the interstitial fluid, then you're pulling water out of blood into the tissue. So both of these forces are pulling forces, right? So then this must mean these are the ones that actually are sort of moving water in the other way, right? So hydrostatic pressure of the interstitial fluid moves water which way?
Into the vessel.
Into the capillary. How about osmotic pressure of the capillary? Moves water into the capillary, right? So out minus in gives you net filtration pressure, right? What if you had more water moving out than back in? Then we get a positive number. So if the net filtration pressure is positive, that means you have water loss from blood into tissues. What if your out minus in is the same? It's zero, which means your net water movement is zero. The net movement is zero. Exactly. So you raise an excellent point. It doesn't mean that the water is not moving. It just means that the net movement is zero. So you might find that a significant amount of water could cross your capillary membrane going out, but if you have the equal and opposite amount of water being absorbed back into your bloodstream, then the net movement is zero. So we said the net filtration pressure is zero. What do you guys think it normally would be? Is it zero? Do you think you always have water movement that's equal and opposite across capillaries? It probably changes. Yeah, it probably changes all the time. In fact, this is one of the reasons why we have a lymphatic system. Remember, going back to A&P, we said the lymphatic system helps pick up excess fluid from tissue and then brings that back to your bloodstream. So if that means we have a whole separate system just to pick up excess fluid, what do you guys think is the normal net filtration pressure of your body's tissues?
Probably on the positive end.
Yeah, it's probably the positive end, right? You have more out than in, which means that you have net water loss into the tissue. So more water leaves than is returned. That's exactly what this is saying. You have more water that leaves tissue than what's returned. This is why we have a lymphatic system. Now, normally this net filtration pressure is pretty low. Like you're talking about like maybe +1, +2. You're not going to lose a significant amount of water across like individual capillary beds. But what's interesting, you guys, is that you lose close to about 2 or 3 liters of water across your capillaries every day. So what is that in relationship to your blood's volume? Yeah, it's close to half. So you're losing close to half of your blood's volume across your capillaries every day. Well, how does it get back to your bloodstream? Otherwise, lymphatic. So your lymphatic system brings it all back. So and that's our next chapter. So next week we'll talk about lymph. Now, what does this look like then, you guys? Well, at the arterial end, we see that blood pressure is higher. At the venual end, it's lower. Do you guys see these arrows here? You have more arrows that are leaving the bloodstream at the arterial end, and then more arrows that are coming back in at the venual end. It's because at the arterial end, net filtration pressure is positive. At the venual end, net filtration pressure is negative. However, you lose more fluid at the arterial end than you reabsorb at the venual end, which basically means that on average, we lose about 3 liters of water out of our blood into our tissues every day, that's a lot of water, right? Now, luckily, we have a lymphatic system that picks up that excess fluid and then brings that back to our bloodstream. Now, what's also nice about this process, you guys, is that it cleans up that fluid along the way, because in your lymphatic system, you got lots of immune cells and lymph nodes, which are kind of like little filters, and it basically cleans up the fluid before it goes back into your bloodstream. So you can also look at this as not necessarily a bad thing. It's actually a way to kind of wash your tissues And by consistently losing some fluid in your tissues and then bringing that back into the lymphatic system, lymph can actually clean this up, and it's returned back into blood. So it keeps your tissues kind of clean and fresh, if that's interesting, if that makes sense. So we said hydrostatic pressure is kind of a pushing pressure. Osmotic pressure is a pulling pressure, right? So you see that hydrostatic pressure can push fluid to a different side. Osmotic pressure can pull fluid to a different side. And we want to have a balance of these pressures. So let's look at the structure of a capillary at the arterial end. What's hydrostatic pressure of the capillary? Good. It's pushing water out of the bloodstream into the tissue. Another word for hydrostatic pressure of the capillary? Blood pressure. You got it. So HPC, hydrostatic pressure of the capillary, is blood pressure. So if you have a really high blood pressure, then you can actually start to have more fluid being forced out of your capillaries. It's interesting. What's osmotic pressure of the capillary? It's a pulling force due to albumin in the plasma. Awesome. Good job. So osmotic pressure of the capillary is because we have albumin inside of our capillary. It can pull water from tissue back into your bloodstream. But you guys see how these are not equal and opposite? You see that we actually lose more water into our tissues than we reabsorb back into our bloodstream. And then our hydrostatic pressure of the interstitial fluid and osmotic pressure, these are almost negligible here, right? So we see that at the arterial end, we have a net water loss, or a net filtration pressure that's positive, which is what it's saying here. We have 10 millimeters of mercury of fluid pressure that's being lost into our tissues. What about at the venule end? Well, we know that blood pressure decreases over time and distance. So we see that hydrostatic pressure of the capillary is now lower than it was before. And osmotic pressure of the capillary is the same because that's just due to albumin. Like, you're not changing the concentration of albumin. So you're still reabsorbing water back into your bloodstream at the venule end. Now, these are also not equal and opposite. But which is the greater force now? Yeah, you're pulling more water in. Exactly. Which means our net filtration pressure is negative. But you guys see this is only -8? Whereas at the arterial end, we had +10. So it means our total net filtration pressure is still positive. So we still lose some water across our capillary into our tissues. And that's why we have a lymphatic system, is to pick up that excess fluid. So it's pretty cool. What if your lymphatic system were blocked? What if it was plugged with like a tumor or parasites? You get edema, right? Because all that fluid that's normally being forced out of your capillaries, if it's not returned, it's just going to start to build up in the tissue. But if that fluid builds up in the tissue and it starts to increase pressure in the tissue, you can force some of it back in. You got it. Because then if you start to get more fluid pressure in like a swollen leg or something, that can start to increase interstitial fluid hydrostatic pressure and start to force more water back into your capillaries. But not enough to reverse the edema, just to kind of limit the amount of edema, if that makes sense. So if these forces aren't well balanced, then what we find is that can lead to edema. So you can see that if you lose albumin and you lose that pulling force, then your net filtration pressure will be super positive. You'll get a lot of edema, right? Or if your blood pressure is really high and you get an increase in that pushing force, you can start to force more water out into your tissues, and that can also lead to edema. Okay, so these are something to keep in mind with respect to sort of fluid movement. Yeah, don't damage your liver. And
Don't damage your kidneys.
yeah, don't damage. Oh man. So okay, guys, let's wrap up with shock. So circulatory shock is basically any conditions where blood vessels are inadequately filled and blood can't circulate normally. And so this is probably a little bit different than what you've heard, like in media. Someone says, "Oh, they're in shock," but they usually refer to that as like emotional sort of. Bless you. They usually refer to that as like an emotional condition, like they're shocked, right? They're in shock. But this refers physiologically to a decrease in blood pressure and a decrease in blood flow that's insufficient to meet your body's metabolic needs. And there's different forms of shock. And I think here we go. So hypovolemic shock, well, hypo means below. Volemic means volume. So hypovolemic shock is where you have such low blood volume that your blood pressure is too low to support adequate blood flow, right? Because we need a pressure gradient for blood to flow from high to low. But if blood pressure decreases, then blood stops flowing. So you get hypovolemic shock with like large-scale blood loss, right? So you can see that with hemorrhagic forms of shock. You can get hypovolemic shock from dehydration too. If you go out and or like hiking in the desert without water, and you get super dehydrated, well, that can also decrease your blood volume, and that can send you into shock. Vascular shock is where you get extreme vasodilation, where due to a variety of circumstances, all the blood vessels in your body just vasodilate. If they vasodilate, then you can decrease resistance so much that your blood pressure basically drops out, right? And there's different things that can cause vascular shock. You guys have heard of like anaphylactic shock. That's due to allergens. Septic shock, that's due to infection, okay? There's also one called neurogenic shock, which is due to damage to the brainstem, where you lose that sympathetic tone and your blood vessels just vasodilate because now you don't have the sympathetic nervous system to stimulate constriction of those vessels, okay? Now, cardiogenic shock results when you have insufficient cardiac output. So you can imagine there's a variety of things that could cause cardiogenic shock, but it's basically where your cardiac output's too low to support normal metabolism in your body.